Hello everyone, this is Vinod Kumar. Today in this video I am going to talk about one of the current trending technology in the digital design called Memristor based in neuromorphic computing. These are the contents that I am going to cover in this video. I am going to talk about fundamentals, what is Memristor and its working principle, how Memristor is going to offer memory, how we can perform logic operations using Memristor, what are bio-inspired circuits, artificial neural networks, how we can implement artificial neural network in hardware. Fundamentals. According to the circuit theory, any electrical system can be characterized by using four fundamental variables. Those four fundamental variables are voltage, current, charge, and the flux linkage. Based on the relation between these four fundamental variables, we have three basic elements called resistor, capacitor, and inductor. Is there any chance for the fourth element? The fourth fundamental element is nothing but memristor, and this is the symbol that we are going to use for the memristor. This is all began when a professor called Lian Cha, who is an IEEE fellow and from University of California, who is to be considered as father of nonlinearity. When he was studying about nonlinear elements like capacitor and inductor, he found out that there is a relation missing between these the four fundamental variables. That is, the relation between a charge and the flux linkage is missing. So after that, he has done some analysis, and in 1971, he came up with an equation relating charge and flux linkage, and the relation he proposed is d phi is equal to m into dq. And the term he used to relate these two variables is called memristor, and the proposed device is called memristor. So what is a memristor? A memristor is nothing but a resistor which is having some memory properties. These are the typical properties of a memristor. The memristor is a nanoscale device. It is a potentiometer with just two terminals. A device with memory, and it's bidirectional, and it offers permanent storage. The memristor is a potentiometer. That means it is going to offer variable resistance. It offers variable resistance for various applied voltages. So it offers a different resistance for a different voltage, different input voltage. The main important property of a memristor is it remembers its previous state value even after the power is removed. That means the memristor is going to remember its resistance value in terms of current. That means it remembers the amount of current that has been flowed through it already. History of current. That is history of current. It offers permanent storage. In future slides, I am going to explain how Memristor offers variable resistance, how Memristor offers memory, and how it offers permanent storage. VI curve. The relation between voltage and current of a memristor is a pinched hysteresis loop. That is, the blue line here is a kind of a Lissajous figure, which is nothing but a pinched hysteresis loop. In 1971, when Liancha proposed that equation, everyone has denied that there is no possibility relating those two variables. But even Liancha has no proof that has no physical proof or any physical device that explains that phenomena relating these two relating these two variables. Even he is not a physicist or an engineer, so that he can he can implement a device to show his work. As he is a mathematician, he was unable to prove his equation. Then, after some years, one of his students called Stephen Kang, along with Liancha, has modified the equation of the memristor, and the equation that they proposed was the equation shown here. What modification they have done is they have included a state variable in their equation. That means the present resistance that the memristor offers will also depends upon the previous states until it's erased. So here V is voltage and I is current and R is resistance, and the state variable is X, which evolves in time. And the relation between the voltage and the current is quasi-isostatic conduction relation. That means it is a very slow process conduction relation. And the resistance depends upon the state of the device. And the state variable evolves in time. We are saying that memristor is a fundamental element. How can we say that the memristor is a fundamental element along with the resistor, capacitor, and inductor? This region here in the third quadrant gives us the fundamental property to the memristor. By using any combination of the resistor, inductor, capacitor, or any other present circuit that we have, it is not possible to achieve this property that is in the third quadrant with the elements that we have. So as it is the only element that is showing this property, so memristor can be considered as a fundamental element. Even Lianja has also proposed a statement: any element that shows pinched hysteresis loop in their VI curve can be considered as a memristor. These are the common semiconductor materials that is used in memristor fabrication. The first one is a titanium dioxide, and the second one is silver silicon, and the third one is silver chalcogenide. So, how does a memristor work? This is a semiconductor material that we are going to use in the memristor fabrication. It has two regions. Those two regions belong to same kind of a material, but what the difference between these two materials is the doping levels. The dark area will have high dopant. That means we can call it as a doped region, whereas the lighter area is an undoped area, which doesn't have abundant number of free charge carriers. Coming to doped area, it has more number of free charge carriers. That means current can easily flow through this area. Then we can say that this area has very low resistance. Whereas the undoped area doesn't have abundant number of free charge carriers, so current can't easily flow through this area. So we can say that this area has very high resistance. So the semiconductor has two areas, with one with a high resistance and one with a low resistance and one with a very high resistance. We say that memristor is a potentiometer. That means it offers variable resistance depending upon the applied input voltage. So if we consider the free charge carriers as holes in the area, then if we apply a positive voltage here, then all holes in this area will be repelled by this positive voltage. So the holes will be moved from doped area to undoped area. As the free charge carriers moves from this area to this area, the area of the doped region increases, whereas the area of the undoped area decreases, causing the total resistance of the system to decrease. Whereas applying a negative voltage attracts all the holes towards this electrode, causing the area of the doped region to decrease, whereas the area of the undoped area to increase, causing the total resistance of the system to increase. This is the way for a different applied voltage, these both regions will change, causing the total resistance of the system to change. This is the principle that is involved in the memristor for offering variable resistance. If here the on resistance is the minimum amount of resistance that the circuit offers, whereas the off resistance is nothing but the maximum amount of resistance it offers for a negative voltage. This is the voltage and the current relation relating these on resistance and off resistance, and width of the doped region and width of undoped region, and D is the total width of semiconductor material. Memristor memory. This is the typical titanium dioxide memristor, which has two platinum electrodes and two areas. The white area is nothing but the undoped area, and the blue area is nothing but doped area which has abundant number of oxygen vacancies. That means here the free charge carriers are nothing but holes. This is the typical cross-sectional view of memristors. Generally the memristor will have a semiconductor film and two electrodes made of a platinum electrode. One is a top electrode and the another one is a bottom electrode. Then we are going to inject some metal ions using electroforming process so that which causes some semi-permanent structural modification. That means we are going to make some structural modifications. That means by using electroforming process, we define both the undoped and doped area regions in the same semiconductor material. So by applying a positive voltages, ions move into the active layer. That means forming a low resistance path. Whereas applying a negative voltage causes ions to migrate out of active layer. That means causing the resistance of the system to increase. How memristor is going to offer memory? Uh, in some semiconductor materials at applied high electric fields, we are seeing that ions are also moving along with free charge carriers to a particular distance, and the distance is depending upon the applied amount of electric field. That means whenever at an applied electric field, we are seeing a coupled motion of ions along with the free charge carriers. One of the important property of the ions is that unlike free charge carriers, they won't move back to their original location even after the removal of electric field. That means ions will be stayed there wherever we put them. That means the movement of ions is permanent. As the ions movement is permanent and the resistance of the device won't change even after the removal of applied electric field, we can say that the memristor offers permanent storage. And this is the diagram that is explaining the flow of ions, the coupled motion of ions with the free charge carriers for a positive voltage and a negative voltage, and for forward biased, reverse biased, and this is the high resistance and low resistance parts. So finally concluding, memristor can be considered as an ion conducting device, and it stores data using ions. And ions, the property, the memristor, the memory property comes for the memristor in terms of ions, whereas they will actually stay wherever we put them. And as the ion movement is permanent, they are going to offer permanent change in resistance. That is means permanent memory. And one more important property is we are going to see those ion movement in only in nanoscale range, not in a micrometer or a millimeter scale. We can only see those movements in only in nanoscale ranges. So we can say that we can say that memristor is a nanoscale device. From this equation, we can also see that the memristor resistance is property is inversely proportional to the distance. As the distance is as the ion movement is smaller and smaller, the resistance of the memristor is also changes very abruptly. So here the total memristor operation can be can be compared to a water pipe. This is some kind of a smart water pipe. Here you can see the diameter of the memristor is large. That means water can easily flow through it. Then we can say that this pipe is offering very less resistance for the water to flow. So if you switch off the water flow, then the diameter of the resistance won't change. Coming to the next one, if the diameter of the memristor, the diameter of the pipe is very less, then the water can't easily flow through this pipe. That means it is offering very high resistance. Even in this case, even the water flow is off, the diameter of the memristor, the diameter of the pipe remains same. That means here we can say that this diameter of the pipe is nothing but a memristor resistance, and the water flow can be considered as a current. This is the formation of ions during low resistance, high resistance, and unprogrammed. And this is a typical cross-sectional view of a silver chalcogenide memristor, which has the two platinum electrodes, and we are going to use silicon nitride and germanium, selenium, metal selenium and silver in order to fabricate this memristor. So what are the advantages that memristor is going to offer? As we are saying that a memristor is an nanoscale device. So in order to perform any operations, we need just a little bit of a voltage or little bit of a voltage. So it offers very less energy consumption, offers great resiliency and reliability. It offers scalability. As the word says that the memristor, we can see this memristor property is only in nanoscale range. So it is possible to fabricate this memristor even in smaller scales like a picometer and etc. It offers multiple states, not only 0 and 1, as it offers a different resistance value for a different output input voltages. If you precisely control the memristor operation, then we can achieve multiple states. One of the main advantage of memristor is we can also perform logic using memristor. In the future slides, I'm going to explain how we are going to perform logic operations using memristor. Memristor logic. The main advantage that we're going to get if we perform logic operations using memristor is we can implement structure that is beyond one human architecture. That means we are going to implement both the logic and the memory circuits in the same die. Unlike our present one human architecture where it uses separate structures for logic and memory and some interfacing circuits in order to connect these, we are unable to achieve high parallel processing powers. Here you can see it is a memristor die, whereas each node is a memristor. Either here these are the inputs and these are the outputs. We are performing a NOR operation and then we are storing it in the next value. We are not going to store the value in some other circuit. We are going to store the value in the same circuit. In this way, we can achieve parallel computing. And we can also implement memristor along with the CMOS layers. So there is a compatibility of a memristor with the CMOS layer also. Memristor polarity. As I already told, for a positive voltage, it offers very less resistance, whereas for a negative voltage, it offers very huge resistance. So this polarity is very important in order to understand how memristor logic circuits is going to how memristor logic circuits works. So these are the circuits for AND gate and OR gate using the memristor, and you can see but just by changing the polarities of this memristor, the operation that the circuits is going to perform will change. So this is where the memristor AND operation can be explained. As you can see, for a logical 0 and logical 0 input, there is no current flow through the circuit. So the output can be also considered as a logic 0. Whereas for a logic 1 and logic 1 input, both the memristor offers very high resistance. Even the total voltage, we can see a logic 1 voltage inside here. So for a 0 and 1 and 0, here I'm considering 1 and 0 inputs. For a 1, the memristor offers very high resistance, whereas for a 0, the memristor offers very less resistance. As you can see here, the polarity is changed. Here we are applying a voltage towards this black terminal, whereas here we are applying the voltage towards other side of the memristor. So that's why for a positive voltage it is offering very high resistance. So for a 1 and 0 case, the output is nothing but the output of this potential divider. That means the output is nothing but R on by R on plus RF into R on plus RF into this input voltage. As the off resistance is very high in terms of mega ohms compared to on resistance, which is in terms of ohms, the ratio is pretty much less than 1. That means we can say the value that we are getting can be considered as a logic 0. This is the way the Memristor works. Coming to our present memory devices, we have three types of memory devices that we are using in our present world. The first one is on-chip cache, which will be on processor memory, where and the main memory can be considered as a random access memory, dynamic RAM, static RAM. And the third one is a mass storage, which is nothing but a typical hard disk and huge amounts of storage. Coming to the cache and the processor, it's very fast, but it is very hard to implement in huge volumes, and it is also very cost. Coming to the second one, spinning hard disks, which are very low at speed but can be produced in a huge amounts and can also be produced at very cheaper price. And coming to the RAM, random access memory has all the moderate features like moderate speed comparing to on-chip cache and this mass storage, and moderate can be produced in moderate volumes, and even the price is also in the between on-chip cache and the mass storage. But our Memristor has all these three features. That means it is very fast and can be produced in huge volumes at very cheaper price. This is the comparison of Memristor with other memory technologies. As you can see, in all the areas, the chip area, energy consumption, read and write times, retention, endurance, 3D capability, Memristor has all the better features compared to present other memory technologies like phase change memory, STT RAM, dynamic RAM, flash, and hard disk. And these results are taken from HP internal research and some public researchers. Memristor types. There are three types of memristors. The first one is molecular and ionic thin film memristor systems, which includes titanium dioxide, polymeric, and magnetic memristor systems. And the second one is spin-based magnetic memristor systems, spinatronic memristors, spin torque transfer magnetic RAM memristors. And researchers are also trying to create three-terminal memristors which offers more controllability than the two terminals. So, current technological challenges. These are the three important challenges that we are facing in our present digital design. The first one is a fabrication. Our present requirements are asking us to implement new kind of a semiconductor technologies at smaller and smaller scales. So it is very difficult to implement semiconductor technologies at a smaller scale because of the lot of limitation. One of the main limitations that we have is the loss of physics. That means uh, speed versus power trade-off. Whenever we need speed, we need more power. So if we want to have less power, then we have to sacrifice speed. So there is always a trade-off between the speed and the power. And the present one human serial architecture, where we are going to use separate structures for memory and logic and some interfacing circuits in order to connect these two. So as there is a time lapse between the memory devices and the logic circuits, we are unable to achieve high parallel processing speeds. So, what is the solution for all these problems? The solution we can get the solution from our nature. The circuits that we are going to build, which whom we got inspiration from our nature, is called bio-inspired circuit, and the computing that we have named it as neuromorphic computing. So instead of thinking of brains as being like computer, researchers wish to make computers more like brains. So why we have chosen a brain? These are the typical characteristics and the capacity of the brain that explains how much how much our brain is complex. That means we can here brain can be considered as a 1 trillion bit per second processor. That means it can process 10 power 12 bits per second, which is which shows how much complex is our brain is. And it has nearly 100 billion neurons, and each neuron is connected up to 10,000 neurons, and nearly we have 1,000 trillion synaptic connections. This is a huge network. And three major characteristics of a brain that distinguishes it from our present supercomputers or maybe present the digital circuits. The first one is low power consumption. Whatever the complex operation that the brain is going to perform, it only needs 20 milliwatts of power. Whereas in order to do the same operation, our supercomputers are taking in terms of thousands of megawatts of power. The second one is fault tolerance. Daily, we are losing our brains losing hundreds to thousands of neurons. But the information stored, the information that is processed in these neurons, we are not going to lose this information. In some way, brain has the capability to transfer the information in those lost neurons to other neurons. Whereas a single fault in a processor may entirely wreck the operation of the supercomputer. The third one is lack of need to be programmed. Our brain learns automatically by itself, whereas our present circuits follow a sequential flow of algorithm. Artificial neural network. So, what are artificial neural networks? Artificial neural network is nothing but a statistical learning algorithm, which are the networks that we had developed, which we got inspiration from biological neural networks like brain, which are used to realize the functions with a very large number of inputs. In this slide, I am going to explain how a neuron passes the information from one neuron to another neuron. A neuron will receive the information from the term called dendrites. Then it has two regions called summation zone and the conduction zone. And the information that it receives from the dendrites will be summed in the summation zone. So the it will be doing summation of all the signal until the summation of the signal will reach a specific threshold value. Whenever it reaches the specific threshold value, and the information is passed on to the axon, and using the synaptic knobs, it will be forwarded to the other neurons. This is the way how information is processed in neuron. So, and one more important property of the brain is it won't give same weightage to different information. That means it provides a different weightage for a different information. How we are going to provide different weightage in our present hardware? It is very difficult to provide this weightage based on the information. So, as we can see, Memristor is offering a different resistance for a different input voltage. That means it is offering, as we can say that it is offering different weightage for a different input. So, and the weightage function is done by synapses in the brain circuit. So, the synapses in the brain can be realized by using these memristors, and the summation function can be done by any summing circuit, and whereas the threshold function can be done by any comparator circuit. This is the way the whole functionality in the neuron can be done in the hardware. The synapses and the neurons that can be considered as active elements, whereas dendrites and axons, which passes the information from one neuron to another neuron, can be considered as passive elements. So the synapses is going to provide weightage function, whereas the neuron will do the summation and the trigger functionalities. So how we are going to implement this artificial neural network in hardware? The first thing that the researchers have tried was to implement everything in the software, because it was very easy to implement and we can implement with a huge number of a capacity. The problems that we are facing is computational complexity. It is very complex, and because of the serial architecture, that means one Neumann bottleneck, we are unable to achieve high parallel processing power, high parallel processing speeds. The better example is when IBM has tried to run a cat's neurocortex on a supercomputer, the simulation run 83 times slower than it intended to be. And the solution they have tried was to implement everything in hardware. And the first thing they have tried was FPGAs, field programmable gate arrays. As FPGAs offers very high speed using very low clock rate, it is very suitable for developing smaller applications. But the problem is they are very costlier, and even they are not scalable in order to implement huge networks like brain. So the obvious solution they are looking towards is a memristor. So as we told, the two functionalities in the neuron are nothing but summation function and the activation function. The summation function can be performed by using a op-amp, whereas the threshold triggering function can be performed by using a comparator, and the weightage function can be performed using memristor. There is a chance that the weightage can be either positive or a negative. So these are the circuits that are going to provide positive and negative weightages for the information. This is a simple memristor, whereas the circuit B, we are going to use the non-inverting feature of op-amp in order to provide the negative weightage, and inverting feature of op-amp in order to provide negative weightage, whereas the non-inverting op-amp will provide positive weightage. This is the way we are going to use the inverting and non-inverting feature of op-amp in order to provide the positive and the negative weightages. And this is a simple circuit that provides both the positive weightage and the negative weightage. As you can see, in the memristor is in the feedback path, which is connected to negative terminal of the op-amp. That means this memristor is responsible for negative weightage for the corresponding input, whereas this resistors will going to provide the positive weightage. So the total synapse, the weightage function, the total synapse, and the neuron function can be achieved by using following these two circuits. The first one is the one we have discussed earlier, which provides both the positive and negative weightages, and this one is an op-amp, which is provide the summation. This is an alternative synapse circuit which provides both the positive and the negative weightages, and these are the memristors. We are going to form a kind of a bridge, which so that based on the applied voltages, only two memristors operates. Like for a positive voltage, Vm1, Vm4 operates in a positive operates, which provides a positive weightage, whereas Vm2 and Vm3 operate for a negative voltage, offers a negative weightage. So a multi-layer network can be considered as a layers of a single layer networks. That means here we are showing an example for a three layer network which consists of three memristors, and we are going to use a programming circuit in order to program this layer network. That means it is a synapse. The synapse functionality can be achieved by using this following circuit. It has three inputs and a programming circuit. So whenever we want to program the memristor to a particular resistance value or to erase the memristor, we are going to use the programming circuit. We are going to take out the memristors from the network, and then we are going to program it, and then we are going to put back the memristor into the network again, so that the total functionality of the circuit will be changed by the programming circuit. And this is the summation function, and this is the activation function. And HP is planning to build a new type of computing machine, which involves they are going to use electrons for processing. That means they are going to use a present CMOS technology for processing. Whereas for a communication, they are going to use photon. That means they are going to use optical silicon photonics for their communication purpose. And for a storage, they are going to use memristor, for which uses ions in order to store the data. And the term they have given for this new computing machine is the machine. And these were some references that I have used in order to make this presentation. Thank you for watching the video.